Why is light itself so painfully slow? Tonight, we're going to explore a measurement that makes even the speed of light seem like a crawl through cosmic molasses. You've probably heard astronomers casually throw around terms like light years and thought you understood cosmic distances. But here's what most people don't realize. Professional astronomers rarely use light years at all. They use something called a parsec, and when you truly understand what a parsec represents, you're going to see our place in the universe in a completely different light. Before we dive in, if you find these kinds of cosmic explorations fascinating, a quick like or a subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Get comfortable. That changes everything. Let's start with something you think you know. Light travels at 186,000 miles per second. Think about that for a moment. In the time it takes you to read this sentence, light has traveled far enough to circle the Earth 7 times complete. That's fast enough to cross the entire United States 50 times in a single second, racing from New York to California and back again over and over without ever slowing down. But here's the thing that should make you pause. In our everyday experience, nothing moves faster than a speeding bullet, a race car, or maybe a jet aircraft. We've built our intuition around these speeds. A car traveling at 60 miles per hour seems fast. A supersonic jet at 1,500 miles per hour feels impossibly quick. Light makes these speeds look like they're standing still. Light could travel from New York to Tokyo and back again, then do it 49 more times, all in the span of a single heartbeat. According to our best understanding of physics, nothing with mass can reach or exceed this speed. It's not just a speed limit, it's a fundamental law of the universe, as unbreakable as the fact that you can't travel backwards in time or create energy from nothing. This speed defines the very structure of reality itself. Einstein showed us that space and time are woven together, and the speed of light is the rate at which this fabric of space-time allows information to travel. Now, a light year represents the distance that light travels in 365 days. That's approximately 5.9 trillion miles. Take a moment to let that number sink in. 5.9 trillion. If you started counting to a trillion, one number per second, it would take you over 31,000 years. And we're talking about almost 6 times that distance, measured in miles. To help you visualize this incomprehensible distance, imagine that each mile was a grain of sand. You would need enough sand to cover the entire island of Manhattan to represent just 1 light year. Picture Manhattan buried under a layer of sand grains, each one representing a mile of empty space. That's the scale we're dealing with when we talk about the distance light travels in a single year. But here's where things get truly humbling. Voyager 1, our fastest and most distant probe, has been racing away from Earth at 37,000 miles per hour since 1977. That's impressively fast, fast enough to cross the United States in 2.5 hours. If you could drive at that speed on the highway, you could go from Los Angeles to New York faster than most people's workday. Yet, even at this remarkable speed, Voyager 1 would need 73,000 years to travel just 1 single light year. Think about that, 73,000 years. That's longer than all of recorded human history. When Voyager 1 was launched, Gerald Ford was president. Personal computers didn't exist, and the internet was just a military experiment. The entire rise and fall of civilizations could happen in the time it would take this probe to cross a single light year of space. Consider what 73,000 years really means. Modern humans have only existed for about 300,000 years. Agriculture began roughly 12,000 years ago. Written language is only about 5,000 years old. The Roman Empire rose and fell in less than 2,000 years. In 73,000 years, our species could evolve into something unrecognizable. By November 2026, Voyager 1 will reach what astronomers call a light day away, where radio signals take 24 hours just to reach the probe from Earth. Imagine trying to have a conversation with someone where every exchange takes 2 full days. Hello, how are you? Send. Wait 48 hours. I'm fine, thanks. That's the reality of communicating across cosmic distances, even relatively small ones. The closest star to our Sun, Proxima Centauri, sits 4.2 light-years away. If you could shrink the distance from Earth to the Sun down to the size of a penny, Proxima Centauri would be nearly 900 feet away, almost 3 football fields. The light you would see from Proxima Centauri tonight actually began its journey in 2021, before the pandemic had officially ended. When you look up at that star, you're literally seeing the past. Think about the implications of this. The light hitting your eyes right now from Proxima Centauri started its journey when vaccine rollouts were just beginning, when many countries were still in lockdown, when the world felt very different than it does today. That photon has been traveling through the void of space for over 4 years just to reach your retina. Our galaxy, the Milky Way, contains roughly 100 billion stars. If you started counting them 1 per second, working 24 hours a day, without rest, without eating, without sleeping, it would take you 3,200 years to count them all. You would need to count continuously for longer than all of recorded human history just to catalog the stars in our galaxy. Every single point of light visible to your naked eye in the night sky is just a tiny fraction of our cosmic neighborhood. A light year already seems incomprehensibly vast. Your brain simply wasn't designed to process distances like this. Mine wasn't either. We evolved to navigate African savannas, to judge whether that rustle in the grass was 10 feet or 50 feet away. Our intuition breaks down completely when confronted with cosmic scales. We can manipulate the numbers mathematically, but we cannot truly feel these distances. But here's the thing that will reshape your understanding completely. Professional astronomers rarely use light years at all. They prefer something called a parsec. And when you understand what a parsec really represents, you'll realize that light years, as vast as they are just the beginning of our journey into cosmic enormity. The parsec emerged from a brilliant geometric method called parallax, first successfully measured by Friedrich Wilhelm Bessel in 1838. Picture this. As Earth orbits the Sun over the course of a year, we observe nearby stars from slightly different positions in space. It's like closing one eye, then the other, and watching how your finger appears to shift against the background. Nearby stars show this same apparent shift against the backdrop of more distant stars, but the shift is impossibly small. We're talking about angles smaller than the width of a human hair viewed from 65 feet away. Bessel spent months carefully measuring the position of a star called 61 Cygni, comparing its location when Earth was on one side of its orbit versus 6 months later when we were on the opposite side. The tiny shift he detected, measured in fractions of arcseconds, revealed the star's distance through pure geometry. An arcsecond is 1/3600th of a degree. To put that in perspective, if you held up a quarter at arm's length, it would span about 1,800 arcseconds across. The parallax shift that Bessel measured was a fraction of that. Imagine trying to detect the width of a human hair from the length of a football field. That's the precision required for stellar parallax measurements. Herbert Hall Turner coined the term parsec in 1913, defining it as the distance at which an object would show a parallax of exactly 1 arcsecond. The word itself is a contraction. Parallax plus arcsecond equals parsec. This geometric precision gives us the parsec, 3.26 light-years, or 19.2 trillion miles. To put this in perspective, if the Earth-Sun distance were 1 inch, a parsec would stretch for over 6.5 miles. Imagine laying down a ruler where 1 inch represents 93 million miles, the distance from Earth to Sun, and then extending that measurement for 6.5 miles down a highway. That's the scale difference between our solar system and a single parsec. The parsec doesn't just represent a larger unit than a light year. It fundamentally redefines what we mean by distance in professional astronomy. This geometric definition makes a parsec 206,265 times larger than the astronomical unit, our standard Earth-Sun distance. It's like comparing the length of your thumb to the distance across several states. Here's something that might surprise you. Not a single star visible to your naked eye in the night sky lies closer than 1 parsec from Earth. Every star you've ever seen twinkling in the darkness, Sirius, Vega, Polaris, Betelgeuse, all of them are separated from us by at least this fundamental cosmic distance. Even Proxima Centauri, our nearest stellar neighbor, sits at 1.3 parsecs away. And despite being our closest neighbor, it remains completely inaccessible to us. Voyager 1 would need 95,000 years to reach Proxima Centauri. During that journey, entire civilizations could rise and fall multiple times. The probe would travel a distance equivalent to 8,700 times Pluto's orbit around the Sun. These numbers reveal a brutal truth about parsecs. They're not just far away. They represent distances that are physically insurmountable with any foreseeable human technology. This distance exposes something profound about our cosmic situation. Within 10 parsecs of our Sun, astronomers have cataloged approximately 500 stars. If our solar system were the Olympic Stadium in Paris, the nearest star would be located in Moscow, over 1,500 miles away. The universe operates on scales where even our fastest spacecraft become glacially slow, where the speed of light itself becomes a limiting factor rather than a liberation. And we're just getting started. Astronomers use kiloparsecs to measure distances within our galaxy, where 1 kiloparsec equals 1,000 parsecs, or 3,260 light-years. Think about that scaling for a moment. We've just established that a single parsec represents an almost incomprehensible distance, 19.2 trillion miles. Now multiply that by 1,000. Our Sun sits approximately 8.3 kiloparsecs from the center of the Milky Way. We live in the galactic suburbs, far from the crowded, energetic core, where supermassive black holes devour matter and spit out jets of plasma that stretch for thousands of light years. If our galaxy were a sprawling city, we'd be living in a quiet residential neighborhood comfortably distant from the chaos downtown. The total diameter of the Milky Way spans roughly 34 kiloparsecs, equivalent to 110,000 light-years from edge to edge. At Voyager 1's speed, crossing our galaxy would require approximately 2.5 billion years of uninterrupted travel. Let me put that timeline in perspective for you. Earth itself won't exist in 5 billion years when our Sun expands into a red giant and consumes the inner planets. Our probe could cross the galaxy, come back, and still have time left over before our planet gets vaporized. This is where parsecs reveal their true nature. They're not simply units of measurement. They're fundamental barriers that confine civilizations to cosmic islands, permanently isolated from one another. This scale makes interstellar travel not just difficult, but fundamentally incompatible with human or even civilizational timescales. Let's consider what it would actually take to travel between stars. Suppose we could build a spacecraft capable of reaching 10% of the speed of light, an achievement that would represent the pinnacle of human technological advancement. At that velocity, the journey to Proxima Centauri at 1.3 parsecs would still take 42 years. Think about what 42 years means in human terms. Passengers who boarded as young adults would arrive as elderly citizens if they lived to see the destination at all. Their children born during the voyage, would spend their entire lives trapped in a metal tube racing through the void. This isn't exploration, it's a multi-generational commitment without historical precedent. But the engineering challenges make even this scenario seem optimistic. The energy required to accelerate a 1,000-ton spacecraft to 10% of light speed equals approximately 450 billion tons of TNT equivalent. That represents 9,000 times all the nuclear energy ever detonated in human history since the invention of atomic weapons. Every nuclear test, every bomb, every reactor that's ever operated, multiply all that energy by 9,000. Chemical fuel is absolutely inadequate for this task. Nuclear propulsion might be theoretically possible, but the amounts of fuel required would be staggering. We'd need to carry our own star's worth of nuclear material. Antimatter propulsion offers the highest theoretical efficiency, but here's the brutal reality. We currently produce nanograms of antimatter annually in particle accelerators around the world. We would need tons of antimatter for interstellar voyages. That's an increase of 20 orders of magnitude from our current production capacity. 20 orders of magnitude. If our current production were a single grain of sand, we'd need a volume of antimatter equivalent to all the beaches on Earth, multiplied by millions. The parsec reveals itself not as a neutral measurement, but as a fundamental physical limit imposed by the laws of the universe on civilizations. It's not that we haven't figured out how to cross these distances yet. It's that the universe appears designed to keep intelligent species isolated from one another. Consider the Pleiades star cluster, that beautiful group of stars visible to your naked eye in the night sky. Those 7 sisters sit at 130 parsecs, or 420 light-years away. Even traveling at the speed of light itself, an impossible dream for anything with mass, the journey would take 420 years. That's longer than the United States has existed as an independent nation. When the light you see from the Pleiades tonight began its journey, Benjamin Franklin was still alive. Our sun resides in the Orion arm of the Milky Way, a spiral structure approximately 3,000 parsecs long. Even traveling at the speed of light constantly, crossing this single spiral arm would require almost 10,000 years of uninterrupted journey. That's longer than all of recorded human history. When this hypothetical light-speed journey would begin, humans were just learning to farm. By the time it ended, entire civilizations would have risen, flourished, and crumbled to dust. Globular clusters orbit the galactic halo at distances between 10,000 and 60,000 parsecs from the center of the Milky Way. These ancient stellar cities, some containing millions of stars packed into spheres just a few dozen light-years across, represent some of the oldest structures in our galaxy. Reaching the nearest globular cluster, even at light speed, would take 30,000 years, longer than all of human civilization. This is what parsecs teach us about our cosmic situation. We aren't just small, we're permanently, fundamentally isolated. The distances are so vast that communication with other civilizations, if they exist, would occur across timescales that render meaningful dialogue impossible. A simple hello and hello back exchange with a civilization just 100 parsecs away would take over 1,300 years. But let's dig deeper into what these distances really mean for the possibility of interstellar exploration. Even if we could somehow overcome the energy requirements, even if we could build generation ships capable of sustaining human life for centuries, we face additional barriers that physics places in our path. At 10% of light speed, our hypothetical spacecraft would collide with interstellar dust and gas with the energy of nuclear explosions. Every tiny particle, smaller than a grain of sand, would hit with devastating force. The kinetic energy of a pebble-sized object striking our ship would equal a nuclear detonation. We'd need shielding massive enough to absorb these impacts, which would add exponentially to our ship's mass, making acceleration even more energy-intensive. The cosmic radiation environment between stars would bombard passengers with levels of radiation that would be lethal within months. We're not talking about the relatively mild radiation that astronauts experience in Earth orbit, protected by our planet's magnetic field. Deep space radiation includes high-energy cosmic rays that can penetrate any shielding light enough to be practical for a spacecraft. And all of this assumes we could even build such a vessel. The engineering challenges of creating a closed-loop life support system capable of functioning for decades without resupply have never been solved. The International Space Station, humanity's most advanced space habitat, requires regular resupply missions and has never operated for more than a few years without major component failures. A generation ship would need to be a completely self-sustaining world, capable of recycling air, water, and waste with 100% efficiency for potentially centuries. It would need redundant systems for every critical function, manufacturing capabilities to replace worn components, and a social structure stable enough to maintain mission coherence across multiple generations of passengers who never chose to make the journey. The parsec emerges as more than a distance measurement. It's a cosmic cage. Not a cage of malice, but a cage of physics. The universe has structured itself in such a way that intelligence appears doomed to evolve in isolation, each species forever confined to its stellar neighborhood. This isolation has profound implications for how we think about life in the universe. If civilizations exist around other stars, they face the same barriers we do. They're trapped in their own cosmic islands, separated by parsecs of void that might as well be infinite for any practical purpose. The galaxy could be teeming with intelligence, and we might never know. But perhaps this isolation serves a purpose. Without the possibility of interstellar conquest or conflict, each civilization must find meaning and purpose within the confines of its home system. We can't look to the stars for salvation or expansion. We must learn to live sustainably within the cosmic territory we've been given. The parsec forces us to mature as a species within the boundaries nature has set. In a strange way, our cosmic isolation might be the universe's greatest gift to intelligence. Free from external threats or distractions, each species gets the opportunity to develop its own unique culture, philosophy, and understanding of existence. The parsec ensures diversity on a cosmic scale. Countless independent experiments in consciousness scattered throughout the galaxy, each following its own evolutionary path through the landscape of possibility. Consider the Orion Nebula, the closest star-forming region to Earth, located approximately 410 parsecs away. This stellar nursery, where new suns are being born from clouds of gas and dust, represents one of the most active and spectacular regions visible in our night sky. If we sent a radio message to hypothetical aliens in that nebula today, the response would take 2,700 years to return to Earth. Think about what 2,700 years encompasses in human history. During that time span, the Roman Empire would rise from a collection of Italian city-states, dominate the known world for centuries, then collapse completely into fragments. The entire arc of one of history's greatest civilizations would unfold before our message even made the round trip to Orion and back. This is what parsecs establish: absolute communicative isolation. Conversations across these distances don't take place over coffee or even over decades. They unfold across millennia. The very concept of dialogue becomes meaningless when separated by parsecs. By the time you receive an answer to your question, the civilization that asked it might have evolved beyond recognition or ceased to exist entirely. Now we need to scale up our thinking even further, because parsecs are just the beginning of cosmic distance measurements. Astronomers use megaparsecs for the truly vast scales of the universe, distances so large that individual galaxies become mere points of light. 1 megaparsec equals 1 million parsecs, or 3.26 million light-years. At this scale, we're no longer measuring distances between stars, but distances between entire galaxies. Our nearest major galactic neighbor, the Andromeda galaxy, sits approximately 780 kiloparsecs away. That's 2.5 million light-years. Reaching Andromeda would require 57 billion years at Voyager 1 speed, roughly 4 times the current age of the entire known universe. Even traveling at the impossible speed of light, the journey would take 2.5 million years, a period during which entire species naturally evolve and go extinct. The light you can see from Andromeda tonight actually began its journey when Australopithecus was walking across the African savanna, before our ancestors had mastered fire or developed language. When those photons started traveling toward Earth, humans didn't exist. The entire evolution from early hominids to modern civilization occurred during the time it took that light to cross the void between galaxies. Parsecs reveal that communication with external galaxies is impossible in any practical or civilizational sense relevant to humanity. You cannot have a meaningful relationship with something that takes millions of years to exchange a simple greeting. The scale completely transcends not just human lifespans, but the lifespans of entire species. But here's something fascinating about these galactic distances. Andromeda and the Milky Way are actually on a collision course. They're destined to merge in approximately 4.5 billion years. During this cosmic collision, however, most stars will pass by each other without ever making contact. This is because parsecs of empty void separate even neighboring stars within galaxies. If you represented stars as tennis balls, the distance between them would be equivalent to thousands of miles of absolute emptiness. Galaxies aren't solid objects. They're mostly empty space with tiny islands of matter scattered throughout. When Andromeda and the Milky Way collide, it will be less like two rocks hitting each other and more like two swarms of gnats passing through one another. Some galaxies dwarf even our impressive Milky Way. The galaxy ESO 383-76, one of the largest known, has a diameter of 540 kiloparsecs, or 1.8 million light-years total. Crossing this single galaxy at light speed would take 1.8 million years, longer than our species has existed on Earth. And this is just one galaxy among trillions in the observable universe. Galaxy clusters contain thousands of individual galaxies distributed across regions 3 to 10 megaparsecs in diameter. The Virgo cluster, the nearest major gravitationally bound structure to us, sits 16.5 megaparsecs away and contains approximately 1,500 cataloged galaxies. A radio signal sent to the Virgo cluster today would only be received 54 million years in the future. During that communication delay, small mammals could evolve into whales, elephants, and eventually human beings on Earth. The entire diversification of mammalian life, from tiny shrew-like creatures to the vast array of species we see today, could occur in the time it takes a simple radio signal to reach Virgo and return. Parsecs amplify cosmic loneliness exponentially. Each increase in scale represents a multiplication of fundamental inaccessibility. When we move from stellar distances to galactic distances to cluster distances, we're not just adding more miles, we're entering entirely different realms of impossibility. Superclusters represent structures so colossal that they contain dozens of galaxy clusters, extending across 100 to 200 megaparsecs typically. The Laniakea supercluster, where we reside, contains approximately 100,000 galaxies distributed across 160 megaparsecs, or 520 million light-years. Our Milky Way, with its 100 billion stars, becomes just one tiny component in this vast cosmic architecture. The Sloan Great Wall represents one of the largest known structures in the universe, a filamentary formation extending 440 megaparsecs across space. Crossing this single structure at light speed would require 1.4 billion years, sufficient time for complex multicellular life to evolve completely from scratch. To put this in evolutionary perspective, 1.4 billion years ago, Earth was inhabited only by simple bacteria. No plants, no animals, no complex cells with nuclei existed yet. The entire development of complex life, from the first eukaryotic cells to flowering plants to dinosaurs to mammals to humans, could unfold during the time light takes to cross this single cosmic structure. These aren't just big numbers we're throwing around casually. These scales represent fundamental limits on what it means to exist as a conscious being in this universe. When structures take over 1 billion years for light to cross, we're dealing with distances that exist outside any meaningful relationship to consciousness, intelligence, or civilization. Between these massive structures lie cosmic voids, regions almost completely devoid of galaxies, extending 50 to 150 megaparsecs across. The Boötes supervoid spans approximately 100 megaparsecs in diameter, a distance that light requires 330 million years to traverse. When light from this void reaches us, it carries information from an era when dinosaurs had not yet evolved and primitive reptiles were just beginning to dominate dry land. Each increment of parsecs adds not just distance, but layers of temporal impossibility that transcend human comprehension completely. We're not just talking about places we can't visit, we're discussing regions of spacetime where the very concepts of visiting or communicating lose all meaning. The universe operates according to a phenomenon called redshift, where light from distant objects gets stretched by the expansion of space itself. This stretching increases proportionally with distance, measured in megaparsecs. Galaxies with a redshift measurement of z equals 1 are approximately 3,000 megaparsecs away, where we see them as they existed 8 billion years ago. These galaxies are receding from us at 240,000 miles per second, 80% of light speed. Even if we could somehow send a light signal toward them today, it would never reach them due to the accelerating expansion of space between us. The universe is literally pulling distant regions away from us faster than light can travel. The Hubble constant measures the rate of universal expansion at approximately 43 miles per second per megaparsec. This means that for every megaparsec of distance, space itself is expanding and carrying galaxies away from us at 43 additional miles per second. At 4,000 megaparsecs distance, galaxies recede at 174,000 miles per second, approaching light speed. Beyond approximately 4,200 megaparsecs, known as the Hubble horizon, objects recede faster than light itself. Parsecs transform from tools that reveal distances into instruments that expose regions of the universe eternally inaccessible to humanity by fundamental physical principle. The observable universe has a radius of approximately 14,000 megaparsecs, or 46 billion light-years, in all directions from Earth. This volume contains approximately 2 trillion galaxies, each one separated from its neighbors by megaparsecs of absolute intergalactic void. If each galaxy were a grain of sand, we would need all the beaches on Earth multiplied by millions to represent the cosmic inventory. Try to picture 2 trillion of anything. If you counted one galaxy per second, working constantly without rest, it would take you 63,000 years just to count them all. And remember, each of these galaxies contains hundreds of billions of individual stars. The Milky Way alone holds roughly 100 billion suns, and it's just an average-sized galaxy among trillions. The light from the most distant galaxies has traveled 13.4 billion years to reach our telescopes, departing when the universe was only 400 million years old, still an infant by cosmic standards. But here's something that might surprise you. Those primordial galaxies are now more than 10,000 megaparsecs away due to the continuous expansion of space during their light's journey. While the light was traveling toward us for 13.4 billion years, space itself was expanding, carrying those galaxies ever farther away. It's like trying to walk toward someone on a treadmill that keeps speeding up. Even though you're making progress, your destination keeps moving away from you faster than you can approach it. Quasars represent some of the most extreme objects in this distant realm, supermassive black holes actively devouring matter at the centers of young galaxies. The most distant known quasars sit more than 9,000 megaparsecs away, appearing as they existed when the universe was less than 1 billion years old. A single quasar can emit energy equivalent to trillions of sun-like stars, all concentrated in a region smaller than our solar system. To put that energy output in perspective, imagine replacing our sun with a quasar. The radiation would instantly vaporize every planet, asteroid, and speck of dust within hundreds of light years. The energy density is so extreme that matter gets accelerated to nearly light speed and ejected in jets that can extend for millions of light years through intergalactic space. Even within our own galaxy, the central supermassive black hole called Sagittarius A star demonstrates how parsecs confine us to cosmic isolation. This monster contains 4.15 million times the mass of our Sun and sits 8,000 parsecs away at the galactic center. Even at this relatively close distance, reaching it at Voyager 1 speed would require 460 million years of continuous travel. Think about that timeline. 460 million years ago, complex life was just beginning to crawl onto dry land. The first forests had not yet grown. Fish were the dominant vertebrates, and no creature larger than a small amphibian existed on Earth's surface. An entire evolutionary epoch could unfold in the time it would take to reach our galaxy's center with current technology. In 2019, the Event Horizon Telescope captured the first image of a black hole, M87 star, located 16.8 megaparsecs away in the Virgo galaxy cluster. This supermassive black hole contains 6.5 billion solar masses and launches jets of superheated plasma, extending 1,600 parsecs into intergalactic space. The energy required to accelerate matter to such speeds and hurl it across such distances defies everyday comprehension. Some radio galaxies dwarf even these impressive scales. Alcyonius, a giant radio galaxy, possesses lobes of radio emission extending 5 megaparsecs across space, larger than many entire galaxy clusters. The energy necessary to create these structures equals converting millions of solar masses entirely into pure radiation over millions of years. These cosmic lighthouses beam across distances so vast that their signals take tens of millions of years to traverse their own structures. When we talk about gravitational waves, ripples in the fabric of space-time itself, we're dealing with yet another manifestation of how parsecs isolate cosmic events from direct human experience. The first gravitational waves detected by humanity in 2015 came from a black hole collision 410 megaparsecs away. That collision released energy equivalent to 3 solar masses converted entirely into gravitational radiation in less than 1 second. The violence of that event, 2 black holes, each dozens of times more massive than our Sun, spiraling into each other at half the speed of light before merging, occurred when complex multicellular life was just beginning to evolve on Earth. The gravitational waves from that ancient cataclysm have been traveling through space for over 400 million years, finally reaching our detectors just as human civilization developed the technology to sense them. Parsecs demonstrate that the most violent and energetic events in the universe occur at distances where human intervention or contact remains absolutely impossible. We can observe, we can measure, We can calculate, but we cannot interact. These cosmic phenomena unfold on scales and timelines that render human presence irrelevant. Dark energy, the mysterious component constituting 68% of the universe, accelerates this expansion against gravity's attractive pull. Dark matter, invisible but gravitationally active, makes up 27% of cosmic content, while ordinary matter, everything we can see and touch, represents merely 5% of the total. If we could somehow perceive dark matter, galaxies would appear wrapped in spherical halos extending hundreds of kiloparsecs around each visible galaxy. Computer simulations reveal that without dark matter's gravitational scaffolding, galaxies would fly apart during rotation, unable to maintain structural cohesion. The visible matter we observe represents just the tip of a vast invisible iceberg of cosmic architecture. The average density of the universe equals approximately 6 hydrogen atoms per cubic yard, a vacuum more perfect than anything we can create in laboratories on Earth. In terms of parsecs, galaxies exist as tenuous wisps separated by vast deserts of nearly absolute emptiness. Matter represents an extraordinarily rare phenomenon in this universe, concentrated in minuscule islands floating in infinite oceans of nothingness. Earth, with its rich and complex biosphere, represents a concentration of organized matter exponentially above the cosmic average. We exist on a world where atoms have assembled into molecules, molecules into cells, cells into organisms, organisms into ecosystems. This level of organization and complexity appears vanishingly rare when viewed against the cosmic background of emptiness. Parsecs quantify not just physical distance, but statistical probability, the likelihood of life emerging and persisting in a vast and hostile universe. If intelligent life proves common throughout the cosmos, the distances measured in parsecs guarantee permanent isolation between civilizations, preventing direct encounters or conflicts. If intelligent life proves rare, parsecs magnify cosmic loneliness, potentially confining humanity to perpetual solitary existence. Both scenarios lead to the same practical conclusion. Humanity must consider itself effectively alone in the observable universe for any relevant time frame. This isolation isn't temporary. It's written into the fundamental structure of spacetime itself. Paradoxically, the parsecs that isolate us also protect us. The same distances that prevent us from reaching other stars also shield us from cosmic threats. Hostile civilizations, if they exist, cannot easily reach Earth. Stellar explosions, black hole formations, and galactic collisions remain safely distant. The cosmic quarantine imposed by parsecs grants humanity time and space to evolve, make mistakes, and learn without external interference. Our radio transmissions from the 1920s have only reached stars within about 100 light-years, or 30 parsecs radius. Within this sphere exist approximately 15,000 stars, a minuscule fraction of our galaxy's 100 billion stellar population. Our electromagnetic presence remains invisible to 99.99% of the Milky Way, and will stay that way for tens of thousands of years. Even if alien civilizations detect our signals, their responses would require decades or centuries to return to Earth. The search for extraterrestrial intelligence has monitored nearby stars within 100 parsecs for decades without confirmed detections. Parsecs establish communication delays that transform interstellar dialogue into archaeology, exchanging echoes across millennia rather than engaging in meaningful conversation. Betelgeuse, the red supergiant star that marks Orion's shoulder, sits 200 parsecs away and represents one of the most fascinating examples of how parsecs both isolate and protect us. This stellar giant, destined to explode as a supernova sometime in the next few 100,000 years, will put on one of the most spectacular shows in cosmic history. When it detonates, Betelgeuse will briefly outshine the entire Milky Way, visible in broad daylight for weeks. But here's what makes the 200 parsec distance crucial. We're positioned at precisely the right distance to witness this cosmic fireworks display safely. If Betelgeuse were closer, the explosion would be catastrophic rather than beautiful. Supernovas within 8 parsecs could sterilize Earth with lethal radiation, stripping away our protective ozone layer and exposing all life to deadly cosmic rays. Fortunately, no supernova candidates exist within this danger zone currently. This protective aspect of parsecs reveals something profound about our cosmic situation. The same distances that confine us to our stellar neighborhood also shield us from the universe's most violent phenomena. We exist in a cosmic sweet spot, close enough to observe the spectacular deaths of distant stars, far enough away to survive them. Yet the isolation imposed by parsecs forces us to confront uncomfortable truths about communication and contact with other civilizations. Even if alien societies detect our earliest radio transmissions from the 1920s, their responses would require decades or centuries to return to Earth. The search for extraterrestrial intelligence has monitored nearby stars within 100 parsecs for decades without confirmed detections. Think about what this means for the possibility of interstellar dialogue. If you sent a message to a civilization 50 parsecs away, the round-trip communication time would exceed 300 years. You would die. Your children would die. Your great-great-grandchildren might live to see the reply. This isn't conversation. It's leaving messages for future generations who may not even remember why the original question was asked. The most optimistic scenario for interstellar communication involves civilizations that persist for thousands or tens of thousands of years, treating message exchanges as long-term cultural projects rather than personal conversations. He imagines societies dedicated to maintaining continuous radio dialogues across centuries, with successive generations taking turns in cosmic conversations that outlast empires. The Egyptian civilization lasted roughly 3,000 years, barely long enough for a single exchange with a civilization 30 parsecs away. These communication timescales force us to reconsider what we mean by contact with alien intelligence. Traditional science fiction imagines real-time conversations, negotiations, cultural exchanges. Reality imposes a different model: slow, patient, multi-generational projects, where each message represents a civilization's attempt to speak across the void to unknown listeners in an uncertain future. But parsecs reveal deeper layers of isolation that go beyond communication delays. They expose the fundamental loneliness built into the architecture of the universe itself. Every star system represents an island of warmth and light, surrounded by an ocean of frigid vacuum. The nearest island to ours lies more than 4 light-years away, a distance that renders casual visits impossible and emergency assistance unthinkable. Consider the psychological impact of this cosmic solitude. Humans evolved as social creatures dependent on community for survival. We've extended this social instinct to imagine cosmic communities, galactic federations, interstellar alliances, universal brotherhoods. Parsecs shatter these comforting fantasies. We are not part of a galactic community. We are castaways on a tiny world, permanently cut off from any neighbors we might have. This cosmic quarantine has shaped every aspect of life on Earth. We evolved in complete isolation from other worlds, developing our unique biosphere, our distinct evolutionary path, our particular approach to consciousness. If life exists around other stars, it has followed equally isolated developmental trajectories, creating forms of intelligence and awareness that may be utterly alien to human understanding. The biochemistry of Earth-based life relies on carbon chemistry in liquid water at temperatures between 32 and 212 degrees Fahrenheit. This seems natural to us because it's all we know, but alien biochemistry might operate in liquid methane at minus 300 degrees or in sulfuric acid at 500 degrees. The isolation imposed by parsecs means we can't know how common our particular approach to life might be. Well, parsecs ensure that if we ever encounter extraterrestrial intelligence, it will represent a completely independent experiment in the organization of matter into consciousness. No shared evolutionary history, no common biochemical foundation, no similar environmental pressures. The distance guarantees that alien life, if it exists, will be truly alien in ways that science fiction often fails to capture. Consider the implications for language and communication. Human languages evolved from the specific acoustic properties of our atmosphere, the structure of our vocal apparatus, the social needs of primate groups. Alien languages might rely on electromagnetic radiation, chemical signals, gravitational waves, or phenomena we haven't imagined. Even mathematical concepts, which we assume are universal, might be organized according to alien cognitive architectures so foreign that mutual understanding becomes impossible. The isolation also affects technological development. Every civilization must independently discover fire, agriculture, mathematics, and the fundamental laws of physics. There are no shortcuts, no technological gifts from advanced neighbors, no galactic internet sharing the accumulated wisdom of ancient species. Each world must climb the ladder of knowledge alone, making the same mistakes, rediscovering the same principles, fighting the same battles against ignorance and superstition. This independence could lead to radically different approaches to science and technology. Where humans developed mathematics based on base 10 counting systems derived from our fingers, aliens might think in base 8 using their tentacles, or base 16 using some other anatomical feature. Where we discovered electricity through amber and magnetism through lodestones, other species might have followed completely different paths to understanding electromagnetic phenomena. The scientific method itself, observation, hypothesis, experimentation, peer review, reflects human psychology and social organization. Alien science might operate according to completely different epistemological principles. Perhaps they discover truth through collective dreaming, or mathematical intuition, or direct sensory perception of quantum phenomena. Parsecs guarantee that these alternative approaches to knowledge remain forever isolated from our own. The parsec-imposed isolation also means that civilizations rise and fall in cosmic solitude. If a species destroys itself through warfare, environmental destruction, or technological catastrophe, no rescue fleet arrives from distant stars. No galactic federation intervenes to prevent extinction. Each civilization bears complete responsibility for its own survival, with no safety net except what it creates for itself. This sobering reality transforms how we should think about humanity's future. Earth represents our only viable home for the foreseeable future, not because we lack ambition to reach the stars, but because the stars lie beyond reach of any conceivable human technology. Parsecs enforce a cosmic environmental ethic. Take care of your world because it's the only one you'll ever have. The psychological burden of this isolation extends to our search for meaning and purpose. Traditional religions often place humanity at the center of cosmic attention, created by gods, watched by angels, destined for cosmic significance. Parsecs suggest a different reality. We exist in cosmic obscurity, unknown and unknowable to any possible observers, responsible for creating our own meaning without external validation or divine oversight. Yet this cosmic isolation carries unexpected benefits. Free from external threats or distractions, Humanity has the opportunity to develop its own unique culture, philosophy, and understanding of existence. We don't need to compete for resources with alien civilizations or conform to galactic standards of behavior. Our cosmic quarantine grants us the freedom to explore every possible path of human development without interference. The James Webb Space Telescope, humanity's most advanced cosmic observatory, can peer billions of light years into space, detecting galaxies that formed when the universe was young. Yet even this remarkable instrument cannot resolve individual planets around the nearest stars. Alpha Centauri, at just over 4 light-years away, remains a point source of light even to our most sophisticated telescopes. We can detect the gravitational wobble that suggests planets exist there, but we cannot see them directly. This technological limitation illustrates another aspect of parsec scale isolation. Even our most advanced instruments struggle to gather detailed information about our immediate stellar neighbors. We know more about galaxies billions of light years away than we do about potentially habitable worlds just a few parsecs distant. The universe willingly reveals its large-scale structure while jealously guarding the secrets of nearby planetary systems. Breakthrough. Starshot, an ambitious project to send tiny probes to Alpha Centauri within 20 years using laser propulsion, represents humanity's most realistic attempt to cross interstellar distances. These nanoscale spacecraft would travel at 20% of light speed, reaching our nearest stellar neighbors in about 20 years. But even if successful, the data transmission back to Earth would require an additional 4 years, and the information gathered would fit on a few computer chips. Such missions, while scientifically valuable, underscore the fundamental limitations imposed by parsecs. We might someday send robotic messengers to nearby stars, but human travel remains impossibly distant. The energy requirements for accelerating even small payloads to relativistic speeds approach the energy output of entire nations. Sending humans would require energy equivalent to the total power consumption of human civilization for decades. The engineering challenges compound exponentially with distance. A journey to a star 10 parsecs away would require not just 10 times the energy of reaching 1 parsec, but exponentially more due to the increased shielding, life support, and redundancy needed for longer missions. At some point, the energy and resource requirements become larger than the total mass energy available in our solar system. Yet this cosmic isolation has profound implications for human psychology and philosophy. We are forced to confront the possibility that consciousness, this remarkable phenomenon that allows matter to contemplate itself, might be extraordinarily rare in the universe. If intelligence emerges only under very specific conditions, and if those conditions are separated by parsecs of empty space, then each instance of consciousness becomes precious beyond measure. The parsec becomes more than a unit of astronomical measurement. It represents the fundamental scale on which consciousness exists in this universe, not the scale of atoms or molecules, where matter obeys quantum mechanical laws, nor the scale of galaxies and galaxy clusters, where gravity shapes cosmic architecture. The parsec occupies the middle ground where intelligence emerges from matter and contemplates its own existence in cosmic solitude. Understanding parsecs transforms our relationship with the night sky. Those points of light aren't just distant suns, they're unreachable islands of possibility, each potentially harboring its own experiments in consciousness, its own struggles with existence, its own attempts to understand the cosmos. We can observe them, study them, wonder about them, but we can never visit them or know them directly. They remain forever foreign, forever mysterious, forever beyond our reach. The parsecs that protect Earth from cosmic dangers simultaneously confine humanity to the only solar system we will ever have practical access to. This dual nature of cosmic distances creates a paradox that defines our entire existence. We are both safeguarded and imprisoned by the same fundamental forces that structure the universe. Interstellar colonization would require a society willing to invest centuries of resources for benefits that distant future generations might eventually harvest. Think about the magnitude of this commitment. We're talking about projects that would span dozens of human lifetimes, requiring continuous political will, economic dedication, and technological advancement across time periods longer than any civilization has ever maintained coherent purpose. Human history demonstrates our profound difficulty in coordinating actions for benefits even decades ahead, let alone centuries or millennia in the future. Consider how challenging it is to address climate change, which affects people living today and their immediate descendants. Now imagine trying to maintain support for projects whose payoffs won't materialize for 20 or 30 generations. The psychological and political challenges dwarf even the technological obstacles. Generation ships represent the most realistic theoretical approach to interstellar travel. Massive vessels where crews would live and die during voyages lasting centuries to reach stars just a few parsecs away. But this concept reveals the true horror of parsec-scale distances. The descendants of the original travelers would arrive at their destination completely culturally disconnected from the civilization that originally sent them. Imagine boarding a generation ship today, knowing that your great-great-great-grandchildren would be the ones to finally see another world. Those future humans would have spent their entire lives aboard the ship. Earth would be a legend to them, a story told by elderly passengers about a blue world none of the living had ever seen. They would have developed their own culture, their own language variations, their own social structures adapted to life in a metal cylinder racing through the void. Relativistic time dilation could reduce the subjective time experienced by the crew, but millennia would still pass on Earth during any complete interstellar journey. At 90% of light speed, the crew would experience roughly half the elapsed time, but reaching Proxima Centauri would still require 7.2 years of ship time, and that assumes we could somehow achieve such impossible velocities. The engineering challenges become even more daunting when you consider the environment of interstellar space. Any collision with a dust particle at relativistic speeds would release energy equivalent to a nuclear detonation. Imagine driving down a highway where every speck of dust hitting your windshield exploded with the force of an atomic bomb. The shielding required to absorb such impacts would add exponential mass to the spacecraft, making acceleration even more energetically prohibitive. The energy requirements spiral into impossibility. Shields massive enough to protect against relativistic collisions would themselves become major portions of the ship's mass. More mass requires more energy to accelerate. More acceleration time increases exposure to hazards. Every engineering solution creates new problems that demand even more extreme solutions. Antimatter propulsion offers theoretically superior efficiency, but the practical challenges remain insurmountable. Current human technology produces nanograms of antimatter annually in particle accelerators. We would need tons of antimatter for interstellar voyages. That represents an increase of 20 orders of magnitude in production capacity, equivalent to improving our current capability by a factor larger than the number of atoms in a human body. Even if we solve the production problem, storing antimatter safely presents nightmarish challenges. Any contact between matter and antimatter results in complete annihilation, converting both into pure energy according to Einstein's famous equation. A single containment failure would vaporize the entire spacecraft and everyone aboard. We're talking about storing the energy equivalent of hundreds of hydrogen bombs in perfect magnetic bottles for decades or centuries. Solar sail technology using powerful lasers might accelerate small probes to relativistic velocities, but this approach requires gigawatt laser arrays operating continuously for years. The Breakthrough Starshot project proposes sending gram-scale nanoprobes to Alpha Centauri in 20 years, but data transmission back to Earth would require an additional 4.2 years, and the information gathered would fit on a computer chip smaller than a postage stamp. The fundamental physics becomes even more restrictive when we consider exotic propulsion concepts. Warp drives and traversable wormholes, while theoretically possible within general relativity, require exotic matter with negative energy density. The amount of negative energy needed to stabilize a traversable wormhole exceeds the total energy content of the observable universe by orders of magnitude. We're not just talking about advanced engineering, we're discussing phenomena that may be fundamentally impossible according to the laws of physics. Parsecs function as practically insurmountable barriers, confining technological civilizations to isolated islands, separated by oceans of absolute void. This cosmic loneliness imposes that advanced species will probably never encounter each other physically, despite potentially coexisting temporally throughout nearby galaxies. The speed of light isn't an arbitrary limitation imposed by some cosmic traffic cop. It's a profound consequence of how space, time, and causality are fundamentally intertwined. Einstein showed us that space and time form a unified fabric where the speed of light represents the rate at which cause and effect relationships can propagate. Exceeding this speed would violate the principle of causality itself, potentially allowing effects to precede their causes. Parsecs exist because the universe possesses a specific mathematical structure, a geometric manifestation of three-dimensional space, combined with Earth's annual orbital motion around the Sun. The parallax method that defines the parsec depends on our planet's movement through space, creating a cosmic baseline for triangulation. This isn't just a convenient measuring stick we invented. It's built into the fundamental geometry of our cosmic situation. A parsec isn't simply very far away. It's far in a manner that fundamentally redefines the meaning of the word distance itself. When we measure distances in miles or even light years, we're still operating within conceptual frameworks related to human experience. Parsecs force us into a realm where distance becomes abstract, where our intuitive understanding of near and far completely breaks down. The scale revealed by parsecs forces direct confrontation with the reality of our fundamentally isolated cosmic position. All human civilizations, every war fought, every empire built, every scientific discovery made, every work of art created, all of it has occurred within a volume of space smaller than a grain of cosmic dust when viewed against the parsec scale architecture of the galaxy. If you could somehow shrink the Milky Way down to the size of the United States, our entire solar system would be smaller than a single atom. On this scale, the complete history of humanity, from the first use of stone tools 300,000 years ago to the present moment, would occupy a fraction of a second in the galactic timeline of billions of years. This perspective shift is more than humbling, it's cognitively overwhelming. Our brains evolved to navigate environments measured in feet and miles, to plan for seasons and human lifespans. We simply lack the neural architecture to truly comprehend parsec-scale distances or billion-year timescales. We can manipulate the mathematics, but we cannot feel these scales in our bones the way we feel the distance from our home to the nearest city. Parsecs demonstrate that communication with alien civilizations would face delays of decades or centuries for simple bilateral message exchanges. A conversation with beings located 100 parsecs away would require 652 years to complete a simple question and answer cycle. The concept of dialogue becomes meaningless across such temporal gaps. Consider what this means for the search for extraterrestrial intelligence. Even if we detect artificial signals from a nearby star system, any attempt at communication becomes a multi-generational project. The humans who send the first reply message will die centuries before any response arrives. Their descendants, living in a completely different technological and cultural context, would inherit the responsibility of continuing a conversation they didn't start with entities they've never encountered. This temporal isolation extends beyond mere communication delays. It affects how civilizations develop, how they understand their place in the universe, how they approach fundamental questions about existence and meaning. Every species capable of contemplating the cosmos must do so in essential solitude, developing their own philosophical frameworks without input from cosmic neighbors. The Parsec reveals that the universe operates according to a principle of enforced independence. Each world where consciousness emerges must find its own path to understanding, create its own meaning, develop its own solutions to existential questions. There are no cosmic mentors, no galactic libraries, no universal guidebooks to help young civilizations navigate the challenges of existence. Interstellar travel at sublight velocities requires generations or centuries, transforming exploration into an unprecedented, multi-generational civilizational commitment. This isn't like the great maritime explorations of human history, where brave sailors could hope to return home with tales of distant lands. Interstellar exploration means sending people into the void knowing they will never see their destination, that their children will grow old and die during the journey, that only remote descendants might glimpse alien suns. Parsecs expose the fundamental tension between human expansionist ambitions and the inexorable physical realities of the cosmos that surrounds and constrains us. We are a species that has always pushed boundaries, crossed oceans, climbed mountains, explored continents. Our entire evolutionary history is one of expansion, migration, and conquest of new territories. But parsecs represent boundaries that cannot be crossed through courage, determination, or even advanced technology. This tension isn't a flaw in the universe's design. It's a fundamental characteristic of a cosmos governed by rigorous, immutable physical laws. The same principles that allow stars to shine, planets to orbit, and atoms to bond together also impose absolute limits on how fast information can travel and how much energy is required to accelerate massive objects. The universe operates according to mathematical rules that care nothing for human ambitions or desires. The distance of a single parsec completely challenges any attempt at comprehension based on terrestrial or planetary experiences. Consider that humanity's fastest probe would require 73,000 years to traverse just one parsec. During that enormous span of time, entire civilizations could arise from nothing, flourish for millennia, create vast empires, develop sophisticated technologies, produce great works of art and literature, then decline and vanish completely before the probe reached its destination. Think about what 73,000 years represents in human terms. Our species has only existed for about 300,000 years total. Agriculture began roughly 12,000 years ago. The oldest continuously inhabited cities are less than 10,000 years old. The entire span of recorded history covers maybe 5,000 years. A journey of one parsec would outlast more than 14 complete cycles of everything we consider human civilization. Within one parsec, you could fit approximately 206,265 Earth-Sun distances, our fundamental orbital reference point. This isn't just a large number, it represents a complete breakdown of human spatial intuition. We measure familiar distances in feet, yards, miles. We can visualize the distance from New York to Los Angeles or from Earth to the Moon. But 200,000 times the Earth-Sun distance, our minds simply cannot process such enormity. The Milky Way contains approximately 100 billion stars distributed across a disk 34,000 parsecs in diameter. Crossing our galaxy from edge to edge would require traveling 34,000 times the distance of a single parsec. If one parsec already exceeds human comprehension, what does 34,000 parsecs mean? We're dealing with mathematical abstractions that have no connection to lived experience. The observable universe contains approximately 14 billion parsecs of radius, a number that transcends any possible attempt at human visualization. Within this volume exist approximately 2 trillion galaxies, each containing billions or trillions of individual shining stars. If you could somehow visit one galaxy per second, it would take you 63,000 years just to tour them all once. And remember, we're talking about galaxies, not individual stars. Light from the most distant galaxies has traveled 13.4 billion years to reach our telescopes, departing when the universe contained only a few hundred million years of history. But those primordial galaxies now lie more than 10,000 megaparsecs away due to the continuous expansion of space during their light's journey toward us. They've been carried away by the universe's growth, even while their ancient photons raced across the void. Parsecs reveal that the cosmos operates on scales where the speed of light, once thought to be infinitely fast, becomes painfully, frustratingly slow. This relative sluggishness creates absolute cosmic horizons, regions of the universe that can never be reached or observed regardless of how long we wait or how advanced our technology becomes. Galaxies beyond approximately 4,200 megaparsecs recede faster than light itself, due to the expansion of space, making them permanently unreachable. No spacecraft, signal, or information sent today will ever reach these galaxies, no matter how patiently we wait for a response. They exist in a realm of cosmic inaccessibility that transcends mere technological limitations. The currently observable universe represents only a fraction of the total universe, which may extend infinitely beyond our accessible horizon. We see only the portion whose light has had sufficient time to reach us since the universe began. Beyond that boundary lies terra incognita on a cosmic scale, realms that may contain trillions more galaxies, exotic phenomena, perhaps even completely different physical laws, but which remain forever hidden from our view. The scale of parsecs reveals that even fundamental concepts like far lose all meaning when confronted with absolute cosmic vastness. A parsec simultaneously appears gigantic by human standards, yet microscopic compared to larger galactic and cosmological structures. It occupies an uncomfortable middle ground between the incomprehensibly large and the truly astronomical. Kiloparsecs measure structures within galaxies, megaparsecs measure distances between galaxies, gigaparsecs measure the cosmic web itself. Each scaling represents a conceptual leap that dwarfs the previous level. A kiloparsec contains 1,000 individual parsecs. A megaparsec contains 1,000 kiloparsecs, or 1 million parsecs. A gigaparsec contains 1 billion parsecs. The mathematical progression quickly exceeds any possibility of intuitive understanding. The largest identified structure in the universe, the Hercules Corona Borealis Great Wall, extends 3,000 megaparsecs across observable space. This structure contains billions of galaxies organized into vast filaments and sheets, challenging theories about cosmic homogeneity on large scales. Light requires nearly 10 billion years just to cross this single cosmic architecture. When we detect this structure through our telescopes, we're observing it as it existed billions of years ago, when the universe was significantly younger and smaller. The galaxies we see forming this great wall have since evolved, merged, or been torn apart by cosmic expansion. We're studying archaeological remnants of cosmic history preserved in light that has traveled unimaginable distances to reach our instruments. Parsecs represent more than mere distance measurements. They constitute direct evidence of humanity's minuscule position in a vast, indifferent cosmos. We exist on a tiny, rocky world orbiting an ordinary star in an unremarkable region of a typical galaxy among trillions of others scattered throughout infinite space. Our entire existence occupies a volume smaller than a mote of dust when viewed against the parsec scale architecture of reality. Each additional parsec, multiplied exponentially, increases the sensation of isolation and insignificance experienced by terrestrial civilization within the known observable universe. Moving from 1 parsec to 10 parsecs to 100 parsecs doesn't just add distance, it multiplies our cosmic loneliness by factors that dwarf human comprehension. We are not just alone, we are profoundly, irrevocably, permanently alone in ways that our evolved social psychology struggles to process. Yet this isolation might represent the universe's greatest gift to consciousness. Free from external interference, threats, or distractions, each world where awareness emerges gets the opportunity to develop its own unique perspective on existence. Parsecs ensure that intelligence evolves in splendid isolation, creating countless independent experiments in consciousness scattered throughout the cosmos. The universe has structured itself to guarantee diversity on the largest possible scales. Every civilization must independently discover the fundamental questions about existence, meaning, and purpose. No species can rely on answers provided by cosmic neighbors or ancient galactic civilizations. Each instance of consciousness must create its own philosophy, develop its own understanding of reality, forge its own relationship with the infinite mystery of existence. This enforced independence shapes not just practical considerations about space travel and communication, but fundamental aspects of how conscious beings relate to their universe. We cannot look to the stars for answers, salvation, or companionship. We must find meaning within the boundaries imposed by parsecs, creating significance from our cosmic isolation rather than despite it. Understanding parsecs requires accepting that human intuitions about distance, time, and scale are fundamentally inadequate for comprehending the real cosmos that surrounds us. Our brains evolved to navigate African savannas, measuring distances in yards and feet, estimating whether that rustling in the grass was 10 feet away or 50. We developed cognitive tools perfectly suited for survival on a single planet's surface, but utterly unprepared for the vastness beyond our atmosphere. Think about how your brain processes the distance from your home to your workplace, or from one city to another. These distances feel manageable, comprehensible, real. You can imagine walking them, driving them, visualizing the landscape between point A and point B. But try to apply this same cognitive machinery to a parsec, 19.2 trillion miles, and your mind simply shuts down. There's no evolutionary precedent for processing such enormity. We attempt to force cosmic scales into terrestrial conceptual frameworks, but parsecs demonstrate that the universe completely transcends these natural mental categories. When we say a parsec is like the distance from New York to Los Angeles multiplied by millions, we're trying to domesticate something essentially wild and incomprehensible. The analogy provides a momentary illusion of understanding, but ultimately fails to capture the true nature of cosmic distance. Consider how we understand large numbers in everyday life. $1 million feels like a lot of money because we can relate it to houses, cars, years of salary. $1 billion becomes harder to grasp, but we might think of government budgets or the wealth of billionaires. But $1 trillion? And we're talking about trillions of miles, not dollars. The number becomes so abstract that it loses all connection to lived experience. Analogies help initially. They give our minds something familiar to grab onto when confronted with the impossible. If Earth were a marble, the sun would be a beach ball 8 city blocks away. These comparisons provide temporary scaffolding for our overwhelmed understanding. But eventually, all analogies collapse under the weight of cosmic reality, because no human experience truly compares to the observed reality of parsecs. Every attempt to make parsecs relatable ultimately reveals the inadequacy of human-scale thinking. We might say that light could circle Earth 7 times in 1 second, cross the United States 50 times per second, travel from Earth to Moon in about 1 second. But even light, moving at the ultimate cosmic speed limit, requires over 3 years to traverse a single parsec. The fastest thing in the universe becomes painfully, frustratingly slow when measured against parsec distances. Light years, though immense, maintain some intuitive connection to human temporal experience. We understand years, we live through them, count them, use them to measure our lives. A light year represents the distance light travels in the time it takes Earth to complete 1 orbit around the Sun. There's something comforting about this unit because it connects to our biological rhythms, our seasonal cycles, our lifespan measurements. But parsecs emerge purely from abstract celestial geometry, divorced from any biological or psychological reference point. They represent distance as pure mathematical concept, stripped of human meaning or emotional resonance. A parsec exists because of the specific geometric relationship between Earth's orbital diameter and the apparent angular shift of nearby stars. It's a unit born from the marriage of spherical trigonometry and stellar observation, beautiful to mathematicians, alien to human intuition. This geometric origin makes parsecs more natural for professional astronomy, but less accessible to popular human understanding. Astronomers work comfortably with these units because they deal with mathematical models and geometric relationships, rather than visceral spatial experience. For them, parsecs become tools, precise, useful, but emotionally neutral. They're measuring sticks in a universe too large for tape measures. Professional astronomers work daily with megaparsecs and gigaparsecs, manipulating these vast scales through equations and computer models. They calculate galactic rotation curves, measure galaxy cluster separations, map the large-scale structure of the universe using these units as routinely as architects use feet and inches. Yet, even after decades in the field, few can truly internalize what these distances mean on a gut level. I've spoken with astronomers who can tell you precisely how many megaparsecs separate the Virgo cluster from the Coma cluster, who can calculate redshift distances and cosmic expansion rates with remarkable precision. But when pressed about what these distances actually feel like, they admit the same cognitive limitation that affects everyone. They understand the mathematics, they can perform the calculations, but they cannot feel these measurements in their bones the way they feel the distance from their office to the parking lot. The human mind can manipulate numbers representing parsecs mathematically. We can add them, multiply them, convert them to other units. Computer software lets us visualize cosmic structures, zoom through simulated universes, fly between virtual galaxies, separated by megaparsecs. But we cannot truly visualize or emotionally process these distances. They remain abstract symbols on paper or screens, never becoming real in the way that a mile-long walk or a 100-yard dash feels real. This represents more than just a scaling problem. It's a fundamental mismatch between human cognitive architecture and cosmic reality. Our brains contain roughly 86 billion neurons, each connected to thousands of others through synaptic networks that evolved to solve very specific survival problems. How do I find food? How do I avoid predators? How do I navigate from this water source to that shelter? These mental tools work perfectly for distances measured in miles, but they break down completely when confronted with parsecs. Parsecs expose a fundamental limitation of human cognition when confronted with physical realities beyond the scales our ancestors experienced evolutionarily. We are cognitive provincials equipped with mental tools adapted for a narrow range of spatial and temporal experiences. Our useful cognitive range probably spans from inches to perhaps hundreds of miles, from seconds to maybe a few decades. Beyond these boundaries, our intuition becomes unreliable and eventually useless. When reality exceeds these evolved parameters, our intuition simply shuts down, leaving us dependent on mathematics and instruments to navigate realms our brains cannot truly comprehend. This isn't a failure of human intelligence. It's evidence of intelligence perfectly adapted to specific environmental challenges that don't include measuring intergalactic distances. However, this limitation doesn't prevent humanity from mapping, measuring, and mathematically understanding structures on gigaparsec scales with remarkable precision. We may not be able to feel these distances, but we can detect them, calculate them, and incorporate them into sophisticated models of cosmic structure. This represents one of our species' greatest achievements, transcending our biological limitations through tools, mathematics, and collaborative effort. Scientific instruments extend human perception infinitely beyond biological limitations, detecting light that has traveled billions of parsecs across space and time. The Hubble Space Telescope and the James Webb Space Telescope function as temporal machines, observing galaxies as they existed billions of years ago when the universe was young, smaller, and very different from today. These instruments let us see farther than our eyes ever could, detect frequencies our nervous systems cannot process, measure distances our minds cannot visualize. Each deep field image reveals thousands of galaxies scattered across the frame, each one separated from its neighbors by megaparsecs of absolute intergalactic void. When you examine these photographs carefully, you realize you're looking at more galaxies than pixels. The image resolution cannot capture the true density of cosmic structures. Every point of light represents hundreds of billions of individual stars, entire stellar civilizations contained within objects too distant to resolve any internal structure. These images demonstrate that parsecs aren't rare or special units reserved for exotic measurements. They represent the basic minimum currency needed to adequately describe the cosmos beyond our immediate neighborhood. In the universe beyond nearby star systems, parsecs become as common and necessary as miles in terrestrial geography. The universe operates on scales where what seems impossibly vast to human experience becomes routine, mundane, standard. This normalization of gigantic scales reveals the true character of the cosmos, predominantly empty space, occasionally punctuated by concentrated matter. The universe isn't densely packed with stars and galaxies like some cosmic metropolis. It's mostly nothing, vast deserts of vacuum occasionally interrupted by tiny oases of substance. Matter represents an extremely rare exception to the cosmic rule of emptiness. Parsecs contextualize terrestrial fragility by showing that no accessible backup plan exists if we destroy our unique ecosystems. Despite being cosmically minuscule, Earth contains the only known biosphere within at least hundreds of parsecs in any direction. We have searched the skies for decades with increasingly sophisticated instruments, analyzed thousands of exoplanets for signs of habitability, and found no definitive evidence of life beyond our world. This apparent singularity confers immeasurable value to our planet and imposes monumental responsibility to protect the life it temporarily harbors. We are not just residents of Earth. We are custodians of the only confirmed experiment in biological complexity within our cosmic neighborhood. Destroying this biosphere would eliminate something irreplaceable and possibly unique in our accessible universe. The nearest replacement might be hundreds of parsecs away, forever beyond our reach. Expansion to other stars cannot serve as a realistic alternative to environmental stewardship. It represents a distant dream that first requires developing a sustainable society here on Earth. The technological challenges of interstellar travel are so immense that any civilization capable of crossing parsecs would necessarily have first mastered the much simpler problems of planetary resource management, ecological balance, and long-term sustainable development. Understanding parsecs teaches that the predictable human future remains inseparably linked to this tiny, cosmically isolated planet. Interstellar colonization belongs to a hypothetical far future that may never arrive given the physics involved. Our immediate destiny, our children's destiny, and their children's destiny unfolds entirely within the confines of our solar system. This isn't a limitation to mourn, it's a reality to embrace and work with, rather than against. The colonization of Mars, the asteroid belt, and the Jovian moons offers challenges sufficient to occupy human ambition for centuries without requiring us to cross currently impossible parsec-scale distances. These local expansions represent stepping stones toward eventual interstellar capability, but more importantly, they provide immediate opportunities for human growth and development within our cosmic neighborhood. Consider what establishing a permanent human presence on Mars would require. We need closed-loop life support systems that can function reliably for decades without resupply from Earth. We must develop technologies for extracting water, oxygen, and building materials from Martian resources. We need to create sustainable food production systems in alien environments with atmospheric pressures less than 1% of Earth's temperatures averaging -80 degrees Fahrenheit, and radiation levels that would be lethal without protection. These challenges, while daunting, remain solvable with current or foreseeable technology. The distance to Mars varies from 35 million to 250 million miles, depending on orbital positions, vast by human standards, but microscopic compared to parsec distances. Radio signals take between 3 and 22 minutes to travel between Earth and Mars, allowing for meaningful communication and coordination despite the delay. The asteroid belt offers even greater opportunities for expansion and resource utilization. A single metallic asteroid just half a mile in diameter could contain more platinum than has ever been mined on Earth, enough rare Earth elements to supply human industry for millennia. The low gravitational environment makes mining and construction much easier than on planetary surfaces. We could build massive space habitats, rotating cylinders miles in diameter that provide Earth-like gravity through centrifugal force. Imagine cities in space where thousands of people live and work, sustained entirely by resources extracted from asteroids and powered by solar energy. These habitats could be constructed at the Lagrange points between Earth and Moon, or throughout the asteroid belt itself. Each habitat would be a complete ecosystem, a closed world capable of sustaining human civilization indefinitely without dependence on planetary resources. The moons of Jupiter and Saturn present additional frontiers within our solar system. Europa, with its subsurface ocean containing more water than all Earth's oceans combined, might harbor indigenous life forms. Titan, with its thick atmosphere and lakes of liquid methane, offers unique environments for scientific study and potential resource extraction. These worlds lie 5 to 10 times farther from the Sun than Earth, but still well within the realm of practical human exploration. These local expansions would teach humanity the essential lessons necessary before we could ever seriously consider interstellar voyages measured in parsecs. We must learn to build truly sustainable closed ecosystems that can function for generations without external input. We need to master long-duration space travel, develop robust space-based manufacturing capabilities, and create stable multi-generational communities that can maintain social cohesion across decades or centuries. Every challenge of interstellar travel exists in miniature within our own solar system, available for testing and refinement. Radiation shielding, life support systems, psychological challenges of isolation, resource extraction and recycling, governance structures for isolated communities. All these problems can be studied and solved using the resources available within a few astronomical units of Earth. Parsecs establish the developmental timeline necessary before humanity could legitimately consider itself a mature, interstellar, spacefaring civilization. The distances force us to grow up as a species to solve fundamental problems of cooperation, sustainability, and long-term thinking before the universe grants us access to larger cosmic playgrounds. This isn't arbitrary cosmic cruelty. It's a natural progression built into the structure of spacetime itself. The isolation imposed by parsecs creates a cosmic classroom where species must prove their capability for long-term survival and wisdom before being granted access to galactic scales. Civilizations that destroy themselves through warfare, environmental destruction, or resource depletion never develop the technologies needed to cross parsec distances. Only mature, sustainable societies could conceivably attempt interstellar exploration, and such societies would have already solved the problems that make interstellar expansion necessary for survival. Meanwhile, intellectual exploration of the cosmos through telescopic observation remains viably rich and infinitely rewarding for human knowledge advancement. Every photon captured from galaxies distant by megaparsecs carries information about the fundamental nature of the universe and our cosmic origins. These ancient light particles have traveled across space for billions of years, carrying messages from the early universe directly to our instruments. When we point our telescopes at distant galaxies, we're not just collecting light, we're harvesting information that has crossed unimaginable distances and time spans to reach us. The spectrum of that light reveals the chemical composition of stars that died before our sun was born. The redshift tells us how fast the universe was expanding when that light began its journey. The polarization contains clues about magnetic fields that existed when galaxies were young. Studying objects at parsec distances has revealed cosmic history, universal chemical composition, and immutable physical laws applicable throughout the known cosmos. We've learned that the same nuclear fusion processes that power our sun also ignite stars thousands of parsecs away. The same gravitational forces that keep planets in orbit around our sun also bind galaxy clusters separated by megaparsecs. The same electromagnetic radiation that we use for communication carries information across the universe with perfect fidelity. The Hubble Space Telescope has observed galaxies more than 13 billion light-years away, thousands of megaparsecs distant, showing us the universe as it existed when it was less than 1 billion years old. The James Webb Space Telescope pushes even deeper into space and time, detecting the first galaxies that formed after the cosmic dark ages. These observations let us witness cosmic evolution directly, watching how galaxies grow, merge, and change over billions of years. Cosmology based on observations of distant parsec-scale structures has discovered accelerating expansion, dark energy, and the flat geometry of spacetime with remarkable precision. These discoveries have transformed human understanding of fundamental reality more profoundly than any physical journey could theoretically achieve. We've learned that the universe is not only expanding, but accelerating, driven by a mysterious dark energy that comprises 68% of all existence. We've discovered that ordinary matter, atoms, molecules, everything we can see and touch, represents only 5% of the universe. The remaining 95% consists of dark matter and dark energy, substances that interact with ordinary matter only through gravitational effects. This means the universe is fundamentally alien to our direct experience, composed primarily of phenomena we cannot see, touch, or directly detect. These revelations came not from traveling to distant galaxies, but from carefully analyzing their light after it crossed megaparsecs of space to reach our telescopes. We've effectively visited the distant universe without leaving Earth's vicinity, using electromagnetic radiation as our courier across impossible distances. Gravitational waves detected by LIGO and Virgo observatories let us feel space-time itself vibrating from collisions between black holes billions of light-years away. Parsecs become intellectual portals for understanding the cosmos, even though they remain physical barriers to direct material exploration. Through mathematical analysis and instrumental observation, we can study phenomena occurring at distances we could never hope to visit. We can model the behavior of matter under conditions that exist nowhere in our solar system, understand processes that require millions or billions of years to complete. This duality defines the human cosmic condition perfectly. Minds capable of embracing the universe intellectually, bodies confined to a minuscule fragment of it spatially. Our consciousness can contemplate structures spanning gigaparsecs, calculate the mass of galaxy clusters containing thousands of individual galaxies, model the behavior of matter falling into black holes millions of times more massive than our Sun. Yet our physical forms remain trapped within a narrow band of habitable space around one ordinary star. The contrast is striking and profound. We can use mathematics to describe the curvature of spacetime around massive objects, predict the orbital decay of binary neutron stars, calculate the eventual fate of the universe trillions of years in the future. But we cannot visit even the nearest star, cannot sample the atmosphere of an exoplanet, cannot directly examine the phenomena we study so precisely from afar. Recognizing this condition doesn't diminish humanity. It properly situates our species within the vast cosmic context that actually exists objectively. We are neither the center of creation nor cosmic afterthoughts. We're conscious observers capable of understanding our place in a universe far larger and older than our biological origins would suggest possible. This represents something genuinely remarkable, rather than depressing. Consider the unlikelihood of our existence from a cosmic perspective. We're made of carbon, oxygen, nitrogen, and other heavy elements that were forged in the cores of massive stars and distributed through space by stellar explosions. The atoms in your body are literally stardust, the products of nuclear fusion that occurred billions of years ago in stars separated by parsecs from our current location. Your consciousness is the universe becoming aware of itself through a temporary arrangement of ancient stellar debris. Parsecs teach humility without nihilism, demonstrating that meaning emerges from consciousness and connection rather than from absolute physical scale. The universe doesn't care about size in the way human psychology might expect. A cluster of neurons generating thought is far more significant than a cluster of galaxies generating only gravitational fields. Consciousness represents complexity and organization that transcends mere spatial extension. A human brain weighing 3 pounds and occupying about 90 cubic inches contains roughly 86 billion neurons, each connected to thousands of others through synaptic networks of staggering complexity. This biological computer can contemplate the origin of the universe, compose symphonies, solve mathematical theorems, and experience emotions like love, wonder, and hope. By any reasonable measure, this represents a more remarkable achievement than a galaxy containing 100 billion stars, but no awareness of its own existence. Modern technology allows us to measure stellar parallaxes of billionths of an arcsecond, mapping individual stars at distances of thousands of parsecs with remarkable precision. The European Space Agency's Gaia spacecraft has measured positions and distances for over 1 billion stars, creating the most detailed three-dimensional map of our galactic neighborhood ever assembled. Each measurement represents a victory over the challenges imposed by parsec scale distances. Contemporary stellar catalogs contain positions, distances, and velocities for billions of stars, each data point conquered against barriers imposed by parsecs. These databases represent one of humanity's greatest intellectual achievements, comprehensive census-taking on a galactic scale. We've transformed our cosmic neighborhood from a collection of mysterious lights into a precisely mapped stellar community with known residents and measured properties. The precision of these measurements is extraordinary. Gaia can detect stellar motions as small as the width of a human hair viewed from a distance of 600 miles. This level of precision allows us to trace the orbital paths of stars around the galactic center, identify streams of stars torn from disrupted satellite galaxies, and measure the three-dimensional structure of our cosmic neighborhood with unprecedented detail. Humanity has transformed parsecs from incomprehensible obstacles into everyday tools of astronomical research within just a few centuries of scientific progress. When Friedrich Bessel first measured stellar parallax in 1838, he was attempting something that seemed nearly impossible with the instruments available. Today, we routinely measure parallaxes thousands of times smaller with space-based instruments mapping the galaxy with precision that would seem magical to earlier generations. This transformation illustrates humanity's capacity to expand cognition through instruments, mathematics, and persistent collaborative scientific effort. We've built extensions for our limited senses that can detect phenomena far beyond biological capabilities. Radio telescopes let us hear the universe's electromagnetic whispers across megaparsecs of space. Gravitational wave detectors let us feel space-time's fabric vibrating from cosmic collisions. Particle accelerators let us recreate conditions that existed when the universe was seconds old. Parsecs have evolved from existential threats into celebrations of human intellectual ambition, confronting the infinite with curious courage. Rather than being intimidated by cosmic vastness, we've learned to measure it, map it, and incorporate it into our understanding of reality. We've proven that biological limitations need not constrain intellectual achievement when supported by technology and mathematical frameworks. However, this celebration doesn't eliminate the fundamental physical reality that parsecs remain insurmountable barriers for foreseeable technology in the near or medium-term future. Intellectual mastery doesn't translate directly into physical access. We can model black holes mathematically without being able to visit one. We can calculate galactic rotation curves without being able to tour other star systems. The universe allows us to understand it from a distance, but guards its secrets against direct physical exploration. The cosmic silence imposed by parsecs isn't emptiness. It's an opportunity for humanity to define its own meaning without external alien impositions. In a universe where parsecs separate civilizations, each conscious species must navigate its existential journey in fundamental solitude until its inevitable end. This isolation forces every instance of awareness to become self-reliant, to develop its own answers to the deepest questions about existence, purpose, and meaning. But solitude doesn't equate to insignificance. Consciousness, capable of comprehending parsecs, represents a rare and extraordinary cosmic phenomenon. Consider what it means for matter to organize itself into patterns complex enough to understand the very distances that confine it. Atoms forged in stellar cores billions of years ago have arranged themselves into neural networks capable of contemplating the spaces between galaxies. Humanity remains statistically insignificant, yet profoundly precious, as a manifestation of consciousness capable of understanding its own cosmic insignificance. This represents one of the universe's most remarkable paradoxes. We are simultaneously nothing and everything, irrelevant on galactic scales, yet irreplaceable as observers capable of giving meaning to cosmic vastness through awareness and comprehension. The numbers tell one story. We're specks of dust on a tiny world orbiting an ordinary star in an unremarkable galaxy among trillions. But consciousness tells a different story. We're the universe becoming self-aware, temporary arrangements of matter complex enough to contemplate infinity, to ask why anything exists at all, to create art, music, literature, and love from the raw materials of stellar nucleosynthesis. Parsecs teach that greatness isn't measured in miles traveled, but in understanding achieved and meaning created consciously. A human mind that grasps the concept of a parsec has accomplished something more remarkable than any journey across interstellar space. The ability to comprehend distances we cannot cross represents a triumph of abstract thought over physical limitation, of consciousness over mere matter. A single parsec contains within its definition the entire history of a civilization that developed geometry, astronomy, and technology precise enough to measure it accurately. From the first human who noticed that stars formed patterns, to Bessel's painstaking observations of stellar parallax, to modern space-based telescopes mapping billions of stars, the parsec embodies thousands of years of accumulated knowledge, curiosity, and intellectual courage. Think about the extraordinary chain of developments required to define and measure a parsec. Humans had to develop mathematical concepts like angles and triangles. They needed to understand that Earth orbits the Sun, not the reverse. They had to build instruments precise enough to detect angular shifts smaller than the width of a human hair viewed from miles away. They needed to develop photography, spectroscopy, and eventually space-based observation platforms. Each astronomical measurement expressed in parsecs represents a triumph of human curiosity over the intimidating vastness of an apparently inaccessible cosmos. When we say a star lies 100 parsecs away, we're not just stating a distance, we're declaring victory over cosmic isolation through the power of mathematical reasoning and instrumental precision. Parsecs transform from physical barriers into monuments to humanity's capacity for transcending biological limitations through abstract mathematical thought. The fact that we understand parsecs, even though we cannot traverse them, demonstrates that consciousness operates in a dimension orthogonal to pure physical scale. Intelligence exists in a realm where distance becomes irrelevant, where minds can reach across impossible gaps through mathematics and electromagnetic radiation. Our brains, evolved to handle distances measured in feet and yards, can nonetheless contemplate structures spanning gigaparsecs. This cognitive leap represents one of the most extraordinary achievements in the history of matter organizing itself into complexity. We are biological computers that have transcended their original programming to engage with realities far beyond their design specifications. Parsecs establish the fundamental human condition. We are a local species with universal ambitions, spatially confined yet intellectually free to explore without boundaries. This condition isn't a contradiction. It's a precise definition of what it means to be human in a vast and indifferent existing cosmos. We are neither purely material nor purely spiritual, but something stranger, conscious matter capable of understanding its own limitations. Earth serves simultaneously as a cosmic prison and protected nursery. Our isolation represents both limitation and sanctuary against distant intergalactic dangers. The same parsec-scale distances that prevent us from easily reaching other worlds also protect us from stellar explosions, gamma-ray bursts, and hypothetical hostile civilizations that might exist around distant stars. This protective isolation allows human civilization to develop at its own pace, free from external pressures that might distort our natural evolution. We can explore different social systems, develop diverse cultures, experiment with various approaches to governance and economics without interference from galactic neighbors who might impose their own values or solutions. Parsecs don't deny the possibility of alien life. They simply ensure that physical encounters remain improbable within timescales relevant to human civilization. If millions of civilizations exist throughout the Milky Way, parsecs guarantee that each evolves in isolation, developing unique cultures and destinies without cross-contamination from neighboring species. This isolation creates a cosmos filled with independent experiments in consciousness, each species discovering its own solutions to the fundamental challenges of existence. Where humans developed mathematics based on base 10 counting, aliens might think in base 8 or base 16. Where we express emotions through facial expressions and vocal tones, other species might communicate through electromagnetic fields or chemical signals. Cosmic diversity emerges, not despite parsec-scale distances, but precisely because of them, creating infinite isolated evolutionary laboratories throughout the galaxy. Each world where consciousness emerges becomes a unique research facility where matter experiments with different approaches to self-awareness, creativity, and meaning-making. Parsecs reveal the universe not as a stage for galactic epics of interacting civilizations, but as a collection of parallel solitary stories separated by unbridgeable voids. Science fiction has conditioned us to imagine cosmic communities, galactic federations, interstellar alliances. Reality presents a lonelier picture, countless isolated islands of awareness, each telling its own story in cosmic solitude. Each conscious civilization becomes a unique experiment in matter, organizing itself to understand its own existence in permanent, fundamental isolation. This isolation isn't cruel, it's necessary for genuine diversity and independence. Without the barriers imposed by parsecs, stronger civilizations might dominate weaker ones, imposing uniformity across the galaxy instead of allowing the flowering of infinite variety. Meaning doesn't emerge from being part of a galactic community, but from creating autonomous significance despite cosmically imposed solitude. We cannot derive our purpose from membership in some vast interstellar civilization because no such accessible community exists. Instead, we must generate meaning internally through our relationships with each other and our attempts to understand the universe that contains us. This responsibility for self-generated meaning represents both burden and opportunity. We cannot blame our problems on alien interference or look to cosmic mentors for solutions. Every challenge humanity faces must be solved through human effort, creativity, and cooperation. Every meaning we discover must be authentic rather than borrowed from more advanced neighbors. Parsecs demand that we abandon fantasies of stellar federations and accept the reality of insular existence in a vast, empty cosmic ocean. But acceptance doesn't equal resignation. Parsecs also reveal that the cosmos remains knowable through light that traverses these impossible distances, carrying information across space and time to reach our instruments and minds. Every photon detected from distant galaxies serves as a messenger that has crossed megaparsecs of space, connecting us intellectually to the cosmos despite permanent physical isolation. These ancient light particles carry the signatures of stellar compositions, galactic velocities, cosmic expansion rates, and the fundamental constants that govern reality throughout the observable universe. Astronomy transforms parsecs from absolute barriers into information channels, allowing us to know the cosmos without needing to traverse it physically. Through spectroscopic analysis, we can determine the chemical composition of stars thousands of light years away. Through gravitational lensing, we can map the distribution of dark matter in galaxy clusters. Through cosmic microwave background radiation, we can study conditions that existed when the universe was only 380,000 years old. Understanding parsecs means reconciling ourselves with physical limitations while celebrating intellectual capabilities that transcend these same fundamental barriers. We cannot visit other stars, but we can understand them. We cannot travel to distant galaxies, but we can model their behavior. We cannot cross the cosmic voids, but we can measure them and incorporate them into our comprehension of reality. This represents the essence of human uniqueness. We are the only known species capable of understanding distances we cannot cross, contemplating times longer than our lifespans, and finding meaning in our own cosmic insignificance. Parsecs define not just astronomical distances, but the boundaries between possible and impossible, between ambition and acceptance, between local reality and universal understanding. The human future, whether measured in parsecs or confined to our solar system, depends fundamentally on choices made here, now, on this singular, temporarily inhabited planet. We cannot escape our cosmic isolation, but we can choose how to live within it. We can create beauty, pursue knowledge, show compassion, and build civilizations worthy of our unique position as conscious observers in an unconscious cosmos. If you're still awake, it's because the content was really good. So take a moment, leave a like, and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.